Hello everyone. Now before I start this topic, I'm assuming that you have a basic understanding of set theory. So what is a relation? A relation is any subset of A cross B, where A and B are two sets, and cross indicates a cross product between A and B. Suppose we have A as 1, 2, and 3, B as 2, 3, 4. Now the Cartesian product between A cross B, between A and B is 1, 2, 1, 3, and 3, 4. So how this works is that every element of A is mapped to every element of B. 1 to 2, 1 to 3, 1 to 4, and then 2 to 2, 2 to 3, and so on for every element of A. Now, a relation R can be a subset, is a subset of A cross B. If we take any element from this set of ordered pairs, then that will be called a relation. Let's say we take the first two elements. So this is a valid relation between A and B. So here I said the term ordered pairs. They are called ordered pairs because the order in which they are written matters. 1, 2 is not the same as 2, 1. In general, A cross B is not the same as B cross A. In B cross A, the first element of the ordered pair will belong to B and the second element will belong to A. Whereas in A cross B, the first element will belong to A and the second element will belong to B. Now we will talk about the different types of relations. First, the empty relation. An empty set phi is a subset of any set. So phi is also a subset of this Cartesian product. This is a trivial case. Another trivial case is the universal relation. In universal relation, the set itself, A cross B, is also a subset of A cross B. It contains all the elements that belong to itself. A relation R can be called reflexive if and only if for every element A that belongs to set A, there exists an ordered pair A, comma A in R. For example, let's say our relation is 1, comma 2, 2, comma 1, and 1, comma 1. Now this is not a reflexive relation because for the element 2, there does not exist 2, comma 2 in the relation. If we added 2, comma 2 to this relation can be called reflexive. I forgot to mention that for reflexive, symmetric, and transitive, we will only be talking about relations in set A. Unlike the previous example in which we were talking about A cross B, replace B with A. So now all the relations will be subsets of A cross A. A relation R can be called symmetric if for every element A1, A2 which belong to R, then must exist A2, A1 in R as well, where A1 and A2 are elements of set A. For example, if we take the relation R 1, 2 and 1, 1, we cannot call this a symmetric relation because for the pair 1, 2, 2, 1 does not belong to R. If we added 2, 1, then we can call this relation symmetric. A relation R can be called transitive if for every pair A1, A2 and A2, A3 which belong to R, A1, A3 must belong to R as well, where A1, A2 and A3 belong to A. For example, if we take R as 1, 2 and 1, 3, then this is transitive. Let's take another example. R is 1, 2 and 2, 2. This relation is also transitive. As you can see, A1 is 1, A2 is 2, and A3 is also 2. This is A1, A2, this is A2, A3, and this is A1, A3 as well. Therefore, this is also transitive. A relation R can be called an equivalence relation if it is a reflexive, symmetric, and transitive relation as well. For example, let's take R as 1, 1. Is this relation reflexive? It is, because for every pair in R, A1, A1 also belongs to R, which is 1, 1 itself. Is this relation symmetric? It is, because for A1, A2, A2, A1 belongs to R as well. Here, A1 and A2 are 1 itself. Is this relation transitive? Yes, it is, because for A1, A2 as 1 and A2, A3 as 1, A1, A3 also belongs to R. All the three ordered pairs are 1, 1 itself. So now this relation can be called an equivalence relation. I would like to tell you a property of an equivalence relation. An equivalence relation on a set A divides the set A into mutually disjoint subsets, which are called equivalence classes, whose union gives the set A itself. So what do I mean by that? Let's say we have a relation A, B such that 4 divides A minus B. So what are the possible pairs that will belong to R? 0, 4, 4, 8, 1, 5, 7, 11. There can be many more pairs that belong to R. Here set A is the set of integers. Now if we consider the set A1 as the elements -4, 0, 4, 8, and so on, 3, 7, and so on. So the relation has divided the set into four disjoint subsets A1, A2, A3, and A4, such that any element of the set A1, A2, or A3, or A4 is not related to any other set. 0 cannot be related to 1, -4 cannot be related to 5, 8 cannot be related to -1, -4 cannot be related to 7. The union A1, A2, A3, and A4 gives the set of integers, which is the set A. Hence, this equivalence relation has divided the set of integers into four mutually disjoint subsets A1, A2, A3, A4, whose union give the set A itself. In the next video, we will be talking about functions and their different types. Thanks for watching.